Thank you for having me here. My name is Volodimir Mitarchuk. So we can see it right here. I'm a first-year PhD student, and my main supervisor is Rémi Hérault. And so I'm going to talk about our article that we submitted to the workshop Learn Out session 2022. And we talk about the DFA simple recurrent network correspondence. Well, it's not really correspondence because we just prove one-way implication in the sense that simple recurrent networks can compute DFAs or simulate DFAs, and so we provide a constructive proof. And then the other part of the article is about limits of gradient descent. So we prove that this particular architecture, so the algorithm that we propose to construct simple recurrent networks to compute DFAs, well, this algorithm will generate a whole class of simple recurrent networks that cannot be learned by gradient descent. And well, I propose that we start by reintroducing simple recurrent networks. Simple recurrent network was introduced by Mr. Ellman in 1990. And so it's a neural network that is designed for operating on sequential data. So if we give ourselves a sequence of vectors of the same dimension, I, and we have an initial hidden state vector, then we have this update rule for the hidden state. And it's quite easy because we perform a linear transformation of the input, then we take the linear transformation of the previous hidden state. We add them together. We add eventually a bias, and which gives us a vector, and then we apply coordinate-wise an activation function. And so the activation function, usually we need it to be a nonlinear and differentiable function. So here we focused on this logistic sigmoidal function, which is defined right here. And well, I introduced the rule for the update of the hidden state. So now we have the rule for the output of our recurrent neural network, which is an affine transformation of the current hidden state, which is then transformed by the activation function. So it's quite easy, quite simple. That's why we call them simple recurrent networks. And so what we know about simple recurrent networks in terms of expressivity is that since 1992, we know that they are Turing complete. It's a result by Ziegelman and Sonntag. But they are Turing complete only in theory, because we require for that infinite precision and unbounded time for the computation, but potentially unbounded time for the computation. So in 2021, Chang and Ziegelman proposed another result about simple recurrent networks, which states that they are Turing complete in finite precision, but they require to store the information of the Turing band, Turing tape, on potentially unbounded number of neurons. So we have another result, but still a little bit unrealistic setup with respect to what we have in regular life, what we need. So the question is, what can they do in finite precision and with a fixed number of neurons? And so empirically, it tends to show, well, we see that empirically they operate closely to DFAs. They tend to be comparable to DFAs. And one of the results that goes in this direction is the result by Ziegelman in 1996 that shows that they, in fact, yes, for every DFA there exists a RNN, that simple recurrent network, that can compute the same function. And well, we proved the same result but the difference is that Ziegelman showed it by existence, and we give a construction, so it's an algorithm. So now I would like to talk a little bit about it. I'm not going to dive into the whole theoretical explanation, the general algorithm, because it's very laborious. I hope that I will manage to build enough intuition with a small example, and then I hope I will convince you that it's very easy to extend it to any type of DFA. So let's take this small DFA with two states and operating on an alphabet with two letters. And so we are going to try to build this SRN right here. And well, the idea of building the SRN is that we just need to build these three matrices. We don't need the biases in this construction. So we need to build the matrix W, U, and O. And so we will start by this matrix W, the matrix of the hidden state transition. And one of the key ideas, the concept is that we are going to use the saturation of the activation function. What do I mean by that is that the activation function in theory is defined by this right here. So we have a function that is defined on the real line, and the target space is an interval, an open interval of 0, 1. And in theory, we never reach the boundaries, but in reality, we do reach them, and in finite precision. And in fact, when we use the regular norm, the regular float numbers that we use on our computers, the EEEI 754 norm, well, we reach the boundaries very, very fast. In fact, if we give an input greater than 89 to the activation function, well, it will output 1. And if the input is smaller than minus 89, well, then we will obtain a 0. And so we are going to use this trick right here to make our computation stable in the simple recurrent network. So we have this binary behavior, and very stable because we have integers, zeros and ones. We don't have any rounding error or something like that. So it's very easy to deal with this stuff. And so well, here we have on this image right here, we see it's this right here is the simple recurrent network that computes exactly the same function right here. So you see there's this parameter J that appears, capital J, and this parameter is a big integer that that we call the saturation parameter. And so this parameter, its job is to take the outputs of this computation inside this linear computation, to take them far enough away from 0 so that we have a number, we always have values greater than 89 or smaller than 89. And so the activation function will always output 0s and 1. And so this will give us very, so this first thing gives us a very convenient behavior for the computation here inside, because we are going to reuse the hidden state. And so if we manage to have zeros everywhere on the coordinates of our hidden state, and only one, only a unique one, or a unique coordinate that is equal to 1, then it will be very convenient to design this matrix right here, such that we will have our desired behavior. We want to simulate the transition function in this hidden state update rule. So let's try to build this intuition on this simple toy example. So let's say we are in the state Q1, and we want to encode on one vector. We want to encode the information about the transition that we have from the state Q1. So we have two transitions. So we have Q1 and B. So the transition will be, we will stay in the state Q1. And so if we have Q1 and we read A, then we will move to the state Q2. So what we will do in this vector, we will divide it into domains. So what I call a domain is a collection of coordinates. So we'll say a domain is labeled by Q1 is this collection of 4 coordinates right here, and then we'll have a domain labeled domain Q2. And so there are 2 domains because we have only 2 states. And so if we imagine that we have n states, so we'll have a huge vector divided in n domains labeled by every state. So then in every domain, we are going to divide it into subdomains, which are subdomains are also collection of coordinates right here. And these every domain will have the number of subdomains equal to the number of states. So every subdomain will be labeled by a state, Q1 and Q2. So you see here under the domain Q1, we have subdomain Q1 and Q2, and under the domain Q2, we have subdomain Q1 and Q2. And so as the same idea, imagine if we have n states, so we'll have n subdomains. And finally, every subdomain will have a certain amount of the same amount of coordinates allocated to it, and it will have the same amount of coordinates as the size of the alphabet. So you see here we have A, B, and so on for every subdomain. And the idea is that, well, you see, I try to use colors to give you the intuition. So if we see a Q, we are in the state Q1 and we see a B, well, then we want to move to Q1. We would like to stay in Q1. So we are going to stay in the domain Q1. If we are in state Q1 and we see A, then we are going to move into the domain Q2. And we're going to move to the state Q2. And so following this particular architecture, we know that we have these two coordinates of interest. We are going to assign them this value -1, and the other coordinates are going to be assigned the value -3. And well, these particular values, why? Because we can now, by choosing a good value to add them, we can flip the sign, because this is the only thing we have to bother. Because you know, the linear part, the linear computation, we want to have a vector. We want to obtain a vector that has strictly positive coordinates or strictly negative coordinates. And then the saturating parameter will do the job to take them far enough away from the 0, and then the activation function will bring them to 0 or to 1. So here -3 is for the reason because if you add 0 to -3, will remain unchanged. If you add 2 to -3, it will have the same sign. It will be -1, but it won't change the sign. But if you have -1, you add 0 to it, it will conserve the sign. And if you add 2 to it, it will flip to the other side. It will become 1, and it will change the sign. And so you see, if we assign, sorry, yes.
If we could go back to the previous slide.
Yes.
So if I understand correctly, in each set of columns, you effectively have, if the green state with the token transitions to the blue state, right? So if middle column with token in right column transitions to the state in the left column, then we place a -1. Is that the rule?
Yes, -1. Yes, the rule is that if we want to the green states transition to the blue state, seeing the red token, then yes, that's right.
So why, for example, have we not marked that Q2 with B leads to Q1?
Q2 to B leads to Q1 because this is the vector that encodes the transition from the state Q1. Then we do the same thing. We have to engineer the same type of vector for the state Q2.
Oh, so why do we have space for Q2 here at all in the middle column?
You mean these parts right here?
Yes.
because they are used in the other vector, and since we have to have this square matrix, so we are forced to use it.
Could you put any value there if you wanted? Could you put 0 or 10 or anything?
I don't know. I just put this neutral value that is not going to change under something. Well, in the next slide, you have an example of how does it work, the computation. Okay. So if we go to to this slide here, you see if we give the B this vector here, we assign this vector to the letter B, and we have alternating 0 and 2, 0 and 2, and we have, in fact, if you look, we begin with 0, then we have 2, and if I go back to this slide here, we have A, we have zeros at the position that corresponds to A and 2s to the position that corresponds to B. And so when we add this vector to the vector that we just designed just above, well, by doing the computation, we have only negative coordinates except just one coordinate that is equal to 1, that is positive. And when we apply the saturation and the activation, we obtain this vector right here, because due to what I explained just before. And well, the second position, well, it corresponds to the red B right here. It was like we wanted to remain in the domain Q1. So no matter where we are, we still are in the domain Q1. And if we assign the letter A this vector right here, so we have also alternating 2s and 0s, but in the other order. And so if we do the computation, we obtain also a vector with negative coordinates except one coordinate. And when we saturate and apply the activation, we will obtain this vector here. And as you can see, we changed the part, well, as I called it, the domain. We moved to the domain Q2. And so since we always have this, the output is a canonical basis vector, which is very easy to compute on a matrix, because when you evaluate a matrix on a canonical basis vector, it will just extract one column. And so for since we need a square matrix, because we always need to maintain the same size for the hidden state vector, we needed to make it square. So we are just going to put together these vectors that were designed for the state Q1. We put them together 4 times in a row because they correspond to the domain Q1. And we designed the same type of vector for the state Q2, and we just put them together 4 times to obtain the domain Q4. It's a very redundant process. It has it's not efficient at all, but it wasn't built in this sense because it's not efficient to compute. Well, I don't know if it's efficient to compute DFAs with simple recurrent networks, but it's a matrix of low rank because it has only two different columns. But yeah, it grows very fastly. In fact, it is the size of this matrix is the size of the alphabet times the number of states squared. So it grows very fastly. That's why we had to use this small, really small example. And else it doesn't even fit on the page. And so yeah, instead of assigning these weird vectors to letters A and B, we just put them together in a matrix, and we use one hot encoding of the letters to select one of the vectors. And so since we are using only hidden state vectors are only vectors from the canonical basis, that means that have zeros everywhere except one unique coordinate that is equal to 1. It will always select just one column, and it brings us to this computation. every time we'll have this one, or a computation for the Q2 vector, and it's very easy to see that we will maintain this rule by moving.
May I
We will
ask?
simulate. Yes.
So, if I understand correctly, the state that in the HT is in fact a one-hot encoding of basically the current state, the previous state, and the previous token as an artifact of how this is implemented.
Yes, it has more information that it should be. Yes, it has this yeah, it
And
has
then,
a little bit more information. Yes.
Okay. And then you have to repeat each state, number of states times number of tokens to account for this repeated information to select it from whichever one of the duplicates was chosen.
Yes.
I see.
Yes, because we have a lot of info. In fact, yes, this hidden state encodes way too much information, but we just didn't manage to simplify it, and it wasn't even in the idea. We wanted to have just something that works. So yeah, it's just redundant information, but it's better to have more than less.
Yeah.
So and for the accepting rule, it's quite easy, because since we have these one hot encoding vectors, these canonical basis vectors, we just have to design this one row matrix where we are going to put minus ones to the positions that are not accepting, and ones to the position that are accepting. Here we have an error because we miss one value, but it still works, and we miss the saturation parameter. So it comes from a previous version of the paper. So I'm sorry, but it still does work, because we are going to have in this computation will give us 1 or -1 multiplied by the saturation parameter that will bring our this activation function to output 0 or 1. And that's all. This is the construction. Well, it's in fact it's laborious to explain, but when you get this thing, it's very easy, I think. And that's for this part of the article. I'm going to move to the finite precision and the gradient descent failure. So a word about finite precision. It was quite important for us. It's quite important to work with finite precision, because it's the closest that we have to the real world. So how do we define it formally? Is that it's numbers on a budget. We have a budget of for the storage. So we'll have this budget for the mantissa. It means that the digit that compose our float number, and then we have the exponent that allows us to move around in the magnitude. So we can work with very, very big numbers and very small numbers. And so we need 1 bit for the sign, because it's a binary information. Then we have a certain amount of digit for the mantissa, for the significant. So these are the digits that compose our number. They have their order. They are ordered, and then we have a certain amount of digit allocated for the exponent. So B represent the basis in which we are working, and so every float number will be represented in this form. It's just product of 3 numbers. And so here we have an example. So let's say that the basis is 10. So we have this minus 12,35, which is written -1 times 1,235 times 10 to the power 1. So it's a very maybe unusual way to write it down, but it is still. And here we have another expression of this same float number. So we don't have a unique way of writing them down, like so it's very handy to do operations algebraic operations on numbers, but still we would like to have one unique representation that we can use for all float numbers, and it will be this one here that we call the normal form of the float number. And it's just we just will position the comma after the first non-zero digit. So in this way, when we talk about float numbers, we will represent them like this. And well, this is just the way we describe it. Finite precision configuration is entirely described by the basis, the number of digit allocated for the mantissa, and the number of digit allocated for the exponent. Right. So if we want to do addition in finite precision, so it might be a little bit counterintuitive sometimes, but well, if we take two numbers, x and z, two float numbers in the same configuration, and we assume that x is strictly greater than z, then if we write them down in this, well, they have their normal form representation right here. And if we want to add them up, well, we have to do this computation right here. And in order to do that, we have to match the exponent. So without loss of generality, we fix the biggest number, and we want to match the smallest one to have, we want to have it the same exponent. So we are going to use this scheme right here. If we want to increment the exponent, we have to add a 0 in the beginning of the mantissa. But what happened, unfortunately, is that we are going to lose the last lambda minus zeta exponents if they are not non-zero values. But we do lose some information. So well, yes. So here we have the computation, and to have a just a small example, let's assume that the space for the mantissa is 4 digits. It's a very small precision that we have here, and we want to add these two numbers here. So you see that they don't have the same exponents. We have 1 and 0, and so it's not equivalent, but let's say it is. We have to do this transformation right here in order to perform the computation to add. So you see, we lost the last digit, we lost the 4, and we are going to have this this addition right here. So it's not brutal like this. It's not like we are making this make them disappear, these numbers, because if it wasn't a 4, it was an 8 or a 7. We should have rounded this 3 to 4, and so we would have an 8 instead of the 8 right here, instead of the 7 right here. So it's not that brutal, but however, we do lose information, and if we have lambda minus zeta strictly greater than the size, the number of digits allocated for the mantissa, well, then x plus z is equal to 0. So if we have here lambda minus zeta greater than m, well, then it does nothing to x. In fact, adding z to x, it doesn't change anything in finite precision. And this, we use this thing right here in our theorem. We use this just because, well, not just because it's, we take the smallest parameter in our neural network, and we consider its magnitude, and so it gives us the epsilon that the gradient doesn't have to be greater. So I will come to this later, but we use this trick right here that there are some magnitudes that don't see each other when we add them together. So let's go to the back propagation through time. So this is the gradient, the propagation of the gradient for the recurrent neural networks. So let's set the decor a little bit. So let's say we are trying to learn simple recurrent networks on a binary classification task. So I recall the update rule, and in this part, I would like to call this update rule the encoder, and the output, I will call it the decoder. So let's say we want to teach our simple recurrent network to recognize a regular language. So we have our alphabet, we have our one-hot encoding that are going to be used for the inputs. We generate words, and so we give a word to our simple recurrent network. It will look at every take a look at every symbol in the word, and in the end, we would like it to give an output close to 1 if the word is in the language, and close to 0 if it's not. So, as I said, the update rule will be named encoder, and the output, the update rule for the output will be named the decoder. And this is a graphical representation of the encoder. So let's say the hidden state vector is of dimension 4. So we have the coordinates of our hidden state vector here, and they are every neuron receives the information from every coordinate, computes the weighted sum, eventually adds a bias, and then performs the activation on it and gives us the output. And we didn't really needed the vector representation from the input, so we represent it like this, and it's just the information that it gives to every neuron, every state. And the decoder, it receives the coordinates from the hidden state vector that was computed, performs a weighted sum, adds eventually a bias, and then computes the activation on it and gives us the response between 0 and 1, float number between 0 and 1. So I just recall what I just said. So we set a language, and we want to train our simple recurrent network R to recognize the language, in the sense that if we have a word, we would like to have the response close to 1 if the word is in the language, and close to 0 if it's not. And what do we mean the response is that if we have a word, it has the length kappa, then the response is the output y kappa, and y kappa is computed by this. So it leads us that we have to compute recursively the hidden state h kappa. And this recursive computation can be represented graphically also, and this is what we do here in this graph. So this picture has a lot of information, but I would like you to focus just on this particular part of the graph right here. So you see, if we give the initial hidden state vector, and we assume that our word is length, kappa is equal to 5, so we are going to produce the first hidden state vector, then the second one, and so on up until kappa. And then when we have our hidden state vector kappa, we perform the decoder on it, and we get the output. And it really looks like a feed-forward neural network. And this analogy is quite not very stupid, because in fact, if we can construct a feed-forward neural network that will give us the same output as this computation right here, when we give on input to this feed-forward neural network the initial hidden state vector. And so performing the backpropagation through time on our recurrent neural network that we want to train is equivalent to performing the backpropagation of the gradient on this feed-forward neural network that we constructed. And so this is just, I think it's a good way of thinking about the backpropagation through time. So if we are going to evaluate our RNN on a word, and then we want to unroll it, so it comes back to just construct this pseudo feed-forward neural network and then propagate the gradient throughout. And so we have the blue arrow represents the forward pass of the neural network, and the green arrow represents the direction of the backwards. So if we look at this neural network from the perspective of graph theory, so we have a directed graph, and when we want to perform the backpropagation, so we are going to reverse the direction, but we still have a directed graph. We just reverse the direction. And so we have our recurrent neural network. We want to teach it. We are going to have a data set with labeled words. And we pick a word, we give it to the RNN, it will perform an output. And then in the end, we want to compare the output to the label. So we're going to use a loss function. And so if we look at our whole computation, it's like adding a node right here and having all this graph, looking at all this graph as as a node. In fact, sorry about that. So adding this node to this graph and considering the whole graph right here. So when we are going to back propagate the gradient, we are going to consider all the partial derivative of this composite function right here. And we use this graph representation to have a good equality right here. So we pick a parameter in the neuron of this color. So we have this neuron here, but you see the difference between this pseudo feed-forward neural network and a real neural network is that in this pseudo feed-forward neural network, we share the same parameter at every layer. So when we talk about a parameter in one neuron, we have to talk about all the representations of this neuron at every layer. So we want to update this parameter wij. So we are going to compute this partial derivative of our composed function. So our RNN composed with the loss function. And we have this pretty representation of a sum of products. So we have products of derivatives because we use the chain rule for computing the gradient, and we have sums because obviously we use linear functions. But here the sum is written in another way because we are doing the sum over a set of paths. So we still use this representation from graph theory. We are going to take all the paths that link our loss node and all the representations of this neuron. So we're going to look at all paths that lead from this node here to this node and to this one and to this one and so on. So and in the product part, we are going to consider the derivatives of the functions. So the nodes of the graph are functions. They are differentiable, so we can consider their derivatives, partial derivatives with respect to the parameter the parameter of interest here. And yeah, so let's say we want to compute the product on the path that links this node and this one here. It's very easy because there is one unique path that lead them together since we have a directed graph. So we have the derivative of the loss function evaluated on the information that was given by the whole graph right here. Then we multiply it by the derivative of the decoder neuron evaluated on the information given by the whole graph that precedes the decoder. And finally, we have the derivative of our node of interest evaluated on the information of the whole on the information that it received from the previous graph, so from the previous computations. So yes, and you see, well, if we want to compute the number of paths that go from this node to this one, it's very easy, it's 1. If we want to compute the number of paths that link the loss node and the nodes above, we will have 4 paths. And if we go one step before, it will be 16 paths. And you see there is this pattern that appears. We have 4 to the power 0, 4 to the power 1, 4 to the power 2. And we have this shape of a geometric series. So we have recipe to control this this sum over here. And now if we put good assumptions on what we see in these derivatives over here, what if we can bound every derivative in the graph, well, then we can control all these parts. We can control this product right here. So this is the recipe that we came up with to control the gradient. And a last remark that I want to make is that you see, when any path that we want to take, it has to start by the loss function, and it has to pass through the decoder neuron. So right here, what we said is just we wanted to, this is a common factor in every product right here. And so to simplify a little bit the theorem, we just bounded it by 1. So I will talk about it later, but we split into 2 parts. We consider this part of the gradient right here, we bound it, and then we bounded every neuron for the rest of the gradient. So the theorem takes this shape right here. So it might be a little bit complex to see it when we are not in the context. I will try to be as clear as possible. But well, we set an epsilon. We want our gradient to be smaller than this epsilon here, and this epsilon is related to the magnitude of the smallest parameter of our network. That means that if even the smallest parameter cannot be updated due to the rounding error, then any other parameter cannot be updated. So that's why we choose our epsilon right here. And then after that, we have requirements about what happens in the neural network. We want that every neuron is saturated up to some point. What do we mean by that is that, you see, if we give inputs to our activation function far enough from 0, we'll have outputs very close to 1 or very close to 0. And so when we take the derivative, we will always have something close to 0. That's why we require this saturation, this amount of a certain amount of saturation for every neuron. And this expression here allows us to have that. So if we have this for every neuron, every linear part of the neuron, then we can derive a bound, this bound right here. So this constant C is going to be a bound, an upper bound for the derivative of every neuron in the encoder part. And then, as I said, we want to get rid of the common part. So we say that the derivative of the loss function times the derivative of the decoder neuron is smaller than 1. We can manage to have an arbitrary number as long as it's not too big. But yeah, we just wanted to have 1 because it simplifies the theorem, simplifies the computations. And then in the end, you see, since the number of paths is this sum over here is related to the size of the hidden state vector. Here we assume that the hidden state vector is size 4. That's why we had this geometric series that pops up, the 4 to the power 0, 4 to the power 1. That's why we have to have a control over the size of the hidden state vector times this constant right here. And so we want it to be smaller than 1 so that the geometric series converges. And we want this, the limit, to be smaller than epsilon. And when we take a look at this, at these requirements like here, it's very easy to put them, and we think it might be very easy to violate them also. But in fact, when we have n equal to 89, and why do I say 89? Because I'm sorry for the disruption, but here I asked to have 89 because we have this saturated behavior. So we have 1s and 0s. So as long as our as long as our neurons, the linear part performs when it outputs something that is greater than 89 in absolute value, so it's far away from 0, well then H, to violate this theorem, we need to have 10 to the power 32 neurons. We have to have this stupidly huge simple recurrent network to violate this this theorem. So in fact, even if these requirements look a little bit too tricky, in some sense, it's, yeah, if we have them, then it's very easy to prove this theorem. But in fact, it's quite hard to not respect the theorem when we have this certain amount of saturation. And well, what is brings us to the conclusion is that when we prove the theorem, well, we can bound the partial derivative, so we can bound every coordinate of our gradient, and it will be bounded by epsilon. And when we use the gradient descent scheme, which is this thing, well, basically it will be doing nothing. And so what we argue is that, well, since the gradient is going to fall at this particular architecture, if we initialize our simple recurrent network, it's with random numbers, and even if we have this perfect data set that will lead us in straight line to the architecture that we want to have, this simple DFA simple recurrent network, well, the gradient scheme will fail before we will have this this illusion of having a local minima before that we reach these architecture. And so we so this theorem exhibits a whole bunch of since we have our DFA to SRN algorithm, well, it exhibits a whole bunch of architecture that cannot be learned by gradient descent. And well, I finished right here. So thank you for your attention, and I hope you have questions.
Thank you. Oh, well, I'll let Marco go before me.
Thanks. Yeah, thanks for the good talk. This is, so to be clear, it's for this construction of DFAs to simple RNNs that you show that this gradient descent will never work. But it's not to say that there's like another construction that you could come up with?
No. Yes. This theorem doesn't prove that it's impossible to learn DFAs. In fact, it doesn't it doesn't have this implication. Well, I think it's not possible because in some sense, if we want to have stable computations, it's very hard. Because fixed points of sigmoidal functions are rare. We don't have that much of them. So I don't know how we can manage to have a stable functioning on arbitrary long strings. So I don't think it's manageable to learn stable DFAs. But this theorem doesn't prove that. So yes.
Cool. Thanks again.
Yeah, thanks for the talk. I had a question about basically the degree to which this relies on the sigmoidal activation function, or whether if you have like a different activation function that's, say, like Lipschitz continuous, you think the same bounds and arguments will go through?
I know that a hyperbolic tangent, it will work also because it has exactly the same shape. So the gradient will have the same shape. I think the constant that we use will move around a little bit. I think we can use it to all types of strictly increasing and bounded functions, I think, or just increasing but bounded functions. Yes.
Have you thought about ReLU at all?
ReLU, the gradient descent. This theorem of gradient descent limit won't work on it because it has the gradient is either equal to 0 or 1, so it's not going to work. But the algorithm above, it works on ReLU also, and it's even easier because we don't even need the saturation activation. We don't need the saturation parameter. We just we just input these numbers, and we will have the same behavior.
Cool. Thanks.
Thank you for the great talk. I would like to ask something maybe a bit simpler. At the end, you showed us your theorem, and you needed some sufficiently large n in order to prove that the gradient would go to 0. And I just wanted to verify what n is. So are we saying if there's too many neurons, it won't learn? Or too many, like too long a sequence? What was the thing that would break it?
What would break the theorem is that if n is not sufficiently large, or we have too much neurons.
What is n?
N is n represents these boundaries. I would like to say yes. I would say yes. That means that we give an input to the activation functions everything that is beyond these boundaries. And so
you're saying once our the activations that we are working with are too saturated effectively, then the gradient goes to 0.
Yes, that's right. Yes. So
and that this n is smaller than the j that you are using. You needed a constant to multiply your representation by in order to make it a finite state machine, right? To achieve the saturation. Yes. And you're saying that there exists an n smaller than that from which the gradient goes to 0?
Yeah. That's right, because if n is equal to 89 right here, well, this value here is very small. It's like it's in order like 10 to the power minus 33 or something like that. It's very, very, very small. So since you have a sigma prime of n times sigma prime at some point, well, this part of the constant is like it's very, very small, and so essentially what we have here is a sigma prime of n, and we use exponential. There's an exponentiation in the definition of the sigmoidal function. So it vanishes to 0 very fast when you take the derivative. Yeah, so you don't even need to go to the 89. What I mean is that if you take 89, which is not a astronomically big number, so if we have saturation up to 89, well, then you have to have to fail this theorem, you have to have this huge amount of neurons, which represents like 10 to the power 70, even more than that, 10 to the power 74, like parameters, which is unachievable in real world. And then maybe you can learn it, but you will never be able to learn it because it's a huge upper bound on what we are able to learn. There are way more simpler things. What I think is this theorem shows that learning architectures, learning RNNs with several that require several saturated neurons is very hard. You're maybe one or two, but if you have very saturated neurons, if you require a lot of saturated neurons for your computation, well, you're going to fail to learn it.
That's really interesting. Thanks.
I have a follow-up question. So if you don't care about getting like full saturation on all these neurons, let's say you only want to generalize to sequences of a bounded length, it seems like you might be able to get away with having I don't know, 80% saturation on several neurons, like, which is doable. And then at some point the gradient goes to 0, so you can't continue to saturate those neurons. But it seems like basically there's some length that you kind of approximate the saturated network up to, and where training can't, like, by training longer, maybe that length is increasing, but what you're showing in some sense is that that length can never go to infinity. Would you say that's a valid way to summarize this, or is that a valid implication from this theorem?
I understand. What do you mean is that if we try to learn an architecture that is partially saturated or almost saturated, is that the
right?
Yes. All
so
right.
Yeah, let's say that you're approaching one of these, like gradient descent is approaching one of the networks from your construction. Like you showed that eventually the gradients will go to 0, so you can't continue along that trajectory. But if you go 80% of the way along that trajectory, you should still approximate the saturated network of that construction for small n, like for small sequence length.
Yes, yes, yeah. I think, well, in this setup, yes, we might approximate this architecture, and it might even fool us because it will perform well on very long sequences. But in theory, it's not going to work as good as the architecture that we proposed, but because it might have some residual computation that will add up when you give arbitrary long strings. So yeah, it's very theoretical. It's not. It's not at all. I don't think it's practical. It's just like, yeah, we wanted to have this gradient descent limitation, but in theory, we don't know if how well it reflects the world. So.
Oh no, I think it's really interesting. And also thinking about, I don't know, I think it'd be cool to think about what happens in the approximate regime, and whether like what the kind of maximum, to what degree that approximation holds or not.
Yeah, we could think about extend a little bit this result about take into account a budget of steps in your gradient descent scheme, and we can think about what does it mean to be stable in computing DFA. So maybe there are other approaches. So I don't know. Maybe further work. Yes.
Okay, well, thank you. That was really interesting. It's nice to see both constructions of saturated RNNs and the realization that we can't actually reach them by learning. And now I'm going to turn the recording off for the more informal chat.